Good morning. I will share my screen. Thank you very much for the opportunity of talking here in this very interesting and nice conference for Lviv. I'm here to talk about how can we apply, for instance, quantum communications in the defense applications and military. Let me just begin my talk, just giving an overview of how important this is. So nowadays, when we are communicating with each other online, for instance, the data is usually encrypted. So in this sense, cryptography is something very interesting and very important for all of us in the way that this can actually protect our information when we communicate and we share data. So the security of these cryptographic systems is usually based on enormous time that is required, for instance, to solve a complex mathematical problem. One of the examples of the cryptography that we use is the RSA, which is widely used, for instance, in public key encryption. Sorry, I had a problem here. Is very used when we use the encryption for our information, and this relies usually on the difficulty, for instance, to do the prime number factorization. So it takes an infinitable amount of time to find a solution to the problem or to randomly guess this key. So in this sense, to encode our information, we mainly have for nowadays two types of encryption: symmetric encryption and asymmetric encryption. In the first method, we only use one key, so in order to encrypt and decrypt our information. On the second one, the asymmetric encryption, we have two keys: a public one that is shared with all the world without compromising the security, and another one that is a private key, which is kept secret. And in this sense, this asymmetric key can be put in some danger when we talk about new technologies like quantum. So we all know that quantum computing is nowadays very a trend, and a lot of countries are trying to develop their own quantum computers. Why this is a kind of a menace or an attack to our system of encrypting information. So quantum computing uses subatomic particles to develop new ways to process and store data, and they are expected to be more faster to actually do some kind of process or computations. So the risks of quantum computing is basically can render our present encryption techniques, and then any nation that invests a lot of money, and there are a lot of them like the US, China, and so on, can actually develop a quantum computer able to break the encryption employed by the other nations. So in this sense, a lot of critical information and infrastructures can have their security attacked. So the vulnerabilities of these crypto systems or communication channels can compromise like a lot of data, from the governmental data, from hospitals, from militaries. So in this sense, we need to protect ourselves with another methods, so then we can encrypt our information, our data, and make it more secure. So one of the ways to do this would be like using quantum key distribution, which is based on the fundamental properties of matter, and it cannot be attacked by any computational means. So in this sense, it is kind of immune to any computational attack, no matter the power of the adversary that is attacking. So since it's a physical method, it requires a physical implementation of the channel, and being quantum requires that the ability to process or transmit or detect signals are also in a quantum level. So, but it's not the only method that we can use. So we have two big areas that are now in the front, just to try to protect your information from a quantum computer. So we have in this one way the post-quantum cryptography, which is based on the same type of mathematical hard assumptions of the usual cryptography, but uses computational problems believed to be even harder to solve for a quantum computer. So these kind of methods are easier to implement, cheaper, and may be the best solution, for instance, in cases of small and mobile devices. But these newly proposed algorithms will require always a continuous evaluation, updates, and replacements as time goes by. So, on the other hand, as I said in the beginning, we have quantum cryptography and quantum key distribution, which their advantage is the quantum mechanics and the laws of physics to ensure that the information is secure. And these kind of protocols provide stronger and long-lived security, but they need dedicated systems with some physical limitations. They can be more useful for applications when you need a long last security, like critical sectors like militaries, governments, hospitals, and so on. So this is a way of securing the exchange of truly random symmetric cryptographic keys between two different parties. So in this sense, the information is encoded in the light from a laser source, and using individual photons. It's based on the principles of quantum mechanics. The exchanged keys are really truly random bits, and the security of distribution process that has a great benefit from the quantum properties. So all this get together enables the symmetrical encryption algorithms. So in Portugal, we have been working very closely with our Ministry of Defense, trying to show how they can use this kind of technologies. And so our first experiment was on the year 2020, with trying to show them with a single link of quantum communication, trying to share a message between two buildings from our militaries that are apart from 4.5 kilometers. And in this way, we were able to show them how they can use it to actually have some secure communications. And this is some kind of start of using these new technologies in the military applications. That nowadays there are a lot of different things that we can use using quantum properties of the matter, going from the communications to the sensing part, to the computing part, but also to another applications that we don't even think. But I think that Mike, after me, will talk more about this part. So, in particular for communications, why this is important for the defense. So we all know that the military operations strongly rely on information and communication services, for instance, for command and control, surveillance, intelligence gathering, and sharing. So these services require a strong and a reliable and secure communication information system network infrastructure. So the present networks that the militaries use are more static and rigid. So whether they should be more dynamic and flexible if we want to think about the picture we've seen before, with all things connected and all things getting manageable in a secure way. So one of the things that we proposed to the militaries and to use the quantum key distribution was the use of the software-defined networks, which will rely on a simple key idea: separation and control of the separation of the control and the data plane, a centralized network policy and programmability, and being more agile, flexible, and easier to manage, meaning that new services, new networks, general devices can be deployed in much faster way than in the old networks. So the architecture using a software-defined network should guarantee in this sense a redundancy and a resilience against the network element failures and network link loss. So basically being prepared for defending to cyber attacks. So we proposed an European project for the European defense, which is discretion, which aims to integrate and combine the software-defined network and the quantum key distribution technology on top of the legacy of optical networks that will build a highly secure, scalable, and resilient network control architecture for the defense networks and for advanced tactical operation services. So discretion combines all these technologies and propose an architecture for this software-defined network, which will evolve in time according to member states' operational needs and ambition. In the project, in particular, 4 member states are participating: Portugal leading, with Spain, Italy, and Austria. And the idea also is to introduce the quantum technologies in Europe as a mechanism of sharing secure information between these different member states. We want also to leverage these member states with the design of different prototypes that can be used in these networks, like the quantum distribution, the cipher machines, even the network. And so this is the main ideas behind the project. So the solution presented, and we are now in a phase of a prototyping, ending the prototyping of the whole network, is reduced in this slide. So basically, we have a benefit situation between these two technologies, the software-defined networks and the quantum key distribution. Whether the software-defined networks are software-driven, programmable, flexible, agile, and interoperable with different technologies like software-defined radios used for communications, but also it's a more easy way of introducing here emerging technologies like quantum. And on the other way, quantum key distribution is based on the fundamental properties of matter and provides the extra physical security to the network. So basically, as I said in the beginning, it cannot be attacked by any computational means. So in the middle, we have the challenge of the military networks. Basically, so the paradigm of the military networks they are separated into parts. One part, which is red, has secure and classified information, and it's can be exchanged and encrypted within the red part. But if we want to exchange something from the red part to the black part, which is insecure and public, we need to encrypt our information so then it's secured to be exchanged. So the project has these 3 main prototypes: three quantum key distribution nodes, software-defined network, and also some cipher machines. The quantum key distribution systems that we are developing are from continuous variables, which can achieve higher secret key rates. And the way the information is encoded and detected is of key importance. So it's in these kind of systems, they are easier and less costly to implement in existing infrastructure. Between the QKD and the network, we will have also the KMS, which is the model that pushes the keys to the main network, and also a software-defined agent that is the element that links the QKD node and the real network. So it will exchange. It is a model that exchanges and monitoring the configuration information. The cipher machines in the project act as the network segregation. So they enable the real-time data protection with hardened and customized systems. So, and they will also consume the keys that are shared and produced by the nodes in order for them to encode or decode, to encrypt or decrypt the information that is passing in the system. So how we are going to use this network and these prototypes in the real world in some use cases? So here we introduced some scenarios in our first phase of the project, going from strategic ones and more static to more tactical and mobile scenarios, which are very challenging for this kind of technology. In this sense, and also studying some requirements and some first design of this system, we came out with our MODs for 3 use cases that we will demonstrate at the end of the project. So these cases are very simple. The first one is an end-to-end encryption use case. It's a link of communication between a point A and B, going from the red part, passing through the black, and then going again to the red. And the crypto models will use the same key to encrypt and decrypt the messages. Then we have a second case, which is an enterprise link encryption, where a node, central enterprise node, will establish some connections with several other nodes. And finally, the automatic management of the keys, which will provide agility to manage the keys of distinct enterprise networks. In order to tackle a first use case in the more tactical scenario, we are also studying in the project the interoperability between the software-defined network and the software-defined radios. So we will have an element in the network, which is a tactical software-defined network controller, which will be responsible for controlling and interacting with the radio's devices based on the policies defined in the different network applications. So we consider 2 scenarios with the radios. One in a setup phase, which is the moment where the devices are being prepared for a mission. And in this sense, they are configured with the proper setup. And then this configuration will include providing different radio-related parameters based on different specification for the mission and loading the proper mission encryption key sets. This setup is taking place inside the secure infrastructure to be developed in the scope of the project, and will use the quantum key distribution to establish the symmetric keys. In a mission phase, this will take place in a tactical environment and will be assumed that all the pre-configurations were applied properly in this setup phase, and then during the mission phase, the radios will establish a control network by the command control center, which is composed by the device, the tactical controller, and the mission control application. So in this sense, the mission control application will manage the network based on this situational awareness, applying the tactical policies and constraints that were defined. So this is kind of our architecture of the network. So we have the control and the associated channels like the QKD nodes tagged as red network elements. So in the limit from the red to the black, we will have the cipher machines. So separating the QKD plane from the black network, and there will be an isolation between the service plane and the whole network, the SDN QKD, constraining the automation and programmability of the black network. Of course, we want to use these elements to create more flexibility, but since these are military networks, we need also to guarantee the resilience and the security of the information. There is a very thorough ongoing analysis in the project between the trade-offs to provide this ample degree of programmability without compromising the security. And also it has been work performed hardly in the project, the way how we evaluate the standards on the technologies. These kind of technologies are new and are new in this field, and so there is a need to study some standardization and some standards for the network, but always taking in mind that we should have security and we should have the resilience of the network. So thinking about the future and how we can connect the different member states in Europe and in particular, we are also studying the possibility of having a hierarchical architecture for these networks. So in a sense, study the interdomain architecture, guaranteeing the network sovereignty on each administrative domain, but also establishing communications according to previously agreements, or allowing different members of a coalition to share information and network resources without losing control of their own networks. But we also studied intra-domain hierarchical network architecture, where we want that they will be easier control of each domain when it's provided, for instance, for a specialized controller, have greater adaptability in the multi-provider scenarios, and have a high available and scalable solution through the distribution of these domain level controls. Also, the project is related with the PESCO project. PESCO projects are different ways of putting all the member states in Europe to collaborate in a specialized field. And in this case, we are linked to this project for the cybersecurity, so the Cyber Academia and Innovation Hub, which is an international center of excellence on cyber defense and cybersecurity, and intends to interconnect different universities, research centers, industry, and other entities and organizations. The project description supports this action, trying to facilitate the research and the investigation of these innovative solutions and technologies for the use of cyber defense, having joined our workshops and training, because it is quite important that the users, the military, would learn more about these technologies and the advantages and benefits of them through the professionals in universities or in the industry working on them. So if they know more about these subjects and these topics, they will actually understand how they can use it on their benefit. Finally, of course, we are talking about militaries, but we need to also relate this with the big infrastructure that has been developed now in Europe, the Euro PCI, which is to safeguard sensitive data and critical infrastructures, integrating quantum-based systems into the existing communication infrastructures. And this will actually provide a security layer based on this quantum physics. The idea is to reinforce the protection of Europe's governmental institutions, so military, the data centers, hospitals, energy grids, and so on, and being one of the main pillars of this cybersecurity strategy for Europe. So this big project, EuroKCI, has two segments: an integrated satellite and terrestrial system that will span all over Europe for ultra-secure exchange of cryptographic keys. The projects are running now also, and in Portugal, we have been also working in the first segment of the Portuguese quantum communications infrastructure, using some of the technology that has been developed in this question. And of course, we will tackle others use cases, more dedicated to the governments and civil sectors. But even so, will be very interesting to test most of the things that we have been also working for the militaries. There are some future plans to construct cross borders between the different member states, but also using the space segment with satellites and optical ground stations in order to, because the limitation on the channels of the quantum key distribution, since we are limited by some distance, even if we use discrete variables or continuous variables. So if you want to link two countries that are separated for a long distance, now then we need to think about something using satellites and the space segment. And I conclude here. Thank you very much for this opportunity.
Yeah, Catarina, thank you so much for being with us for this fascinating talk. So, are there any questions from audience here or online? Do we have questions? Yes.
Good morning, Catarina. It's Alexa.
Morning.
Nice to see you, and also I'm hope that we can meet in person next year in the Lviv Quantum Day 2. And the question is about the technology readiness level. So, what is the technology readiness level of your project? What do you see?
Yes. It's the idea of the project is mainly to develop prototypes. So the technology for now it's low. It's like around 4 or 5 mostly. But also we have prospects of evolve this in a more readiness level in future projects. And also expecting that the EuroKCI will allow us also to evolve a little bit more the prototypes.
Thank you. But if you have provided the demonstration, it's at least 6 level. So I guess it's 6 and higher. Thank you.
Yeah.